Now here's a description of the next special distribution we're going to look at. So consider a random experiment consisting of n independent Bernoulli trials, each with success probability p. Let the random variable x be the number of successes in the n trials. So this is a generalization of the Bernoulli distribution, where we, in that situation, looked at only one trial. Here we've got n independent trials, and x is counting the number of successes in those n trials. And so we want to specify identify the sample space of the random variable x. We want to specify the probability mass function. Think about the cumulative distribution function. And again, find the mean, the variance, the standard deviation, the skewness and kurtosis, and the moment generating function as well. So we've got n independent Bernoulli trials. X is counting the number of successes in those n trials. And so the number of successes, the sample space of x, can be 0, 1, 2, and so forth up to little n. All right, and so that's what the sample space is. It consists of the integers from 0 up to the number of trials, which again is lowercase n. Denote the PMF of x by lowercase f. Then it turns out that it is very similar in form to the PMF of the Bernoulli distribution, the only difference being this quantity out here in front, the n choose x, which we've seen in the context of counting, and in particular in the context of counting combinations. So for values of x in the sample space, the integers from 0 up to little n, the expression for the PMF is equal to n choose x times p raised to the x power times 1 minus p raised to the n minus x power. And for any other value x, for any value of x that is not in the sample space, the PMF would be defined to be 0. Now to communicate this, if we wanted to communicate that x has a binomial distribution based on n trials and success probability p, then we would express that this way. Again, that tilde is the conventional way in statistics to abbreviate the phrase or the expression is distributed as or has this distribution. Okay? Now, you're going to be working with this distribution in an upcoming lab assignment, and so I'm going to leave the work of deriving the various distributional characteristics to you in the context of that lab assignment. So I'm not going to say anything more about that, at least not in this lecture video. Now, skipping ahead in the notes a bit, we're not going to be able to cover all of the distributions that I've got listed in the notes. What we're going to cover in this lecture video are the distributions that I typically cover in the course. And so the next distribution we're going to look at is the exponential distribution, which is the distribution of a particular type of continuous random variable. And so for this distribution, the sample space is the set of positive real numbers, so the interval from 0 up to positive infinity, the open interval, so it does not include the endpoints. The probability density function for the general exponential distribution is as follows. For values of x that are greater than 0, in other words, for values of x in the sample space of this distribution, of this random type of random variable, then the expression for the PDF is 1 over lambda times, and lambda is it's a parameter for this distribution, and it has to be a positive real number. And so it's 1 over lambda times e raised to the negative x over lambda. And then for any value of x that is less than or equal to 0, the PDF would evaluate to 0. And so I want you to think about what does this distribution look like? We're going to be doing quite a bit of work with this. Now, if we wanted to communicate that a random variable x, a continuous random variable x, has an exponential distribution with parameter lambda, then we could either state that in sentence form like this, or we could just state it in an abbreviated form like this. So this is going to be very typical type of notation or abbreviation that we're going to be using. Particularly when we're talking about and utilizing named distributions. And so let's continue on now. And so we've been given the PDF. We have not derived it. All right, we're not going to. We're not really in a position in this course with the level of the prerequisites to derive it, but we will. From that expression for the PDF, we'll derive the CDF, and then we're going to compute or derive formulas for the mean, the variance, the standard deviation, and so forth. And we'll also derive the moment generating function. And then we're actually going to use the moment generating function to come up with formulas for the mean, the variance, and so forth. And we'll talk about that subsequently. So before we begin, I just wanted to point something out, a mathematical result involving the exponential function. You'll remember from your calculus class that the derivative with respect to x of the exponential function evaluated at b times x, in other words, the derivative with respect to x of e raised to the b times x power is equal to b times the exponential function evaluated at b times x. And so the antiderivative of this function here, b times e, the exponential function evaluated at b times x, in other words, the indefinite integral of that function is just the exponential function evaluated at b times x. When we talk about the antiderivative, what we're asking is what function is it whose derivative is b times e to the bx power? And that function, as we've just shown, is e to the bx. And so the antiderivative, or the indefinite integral of b times e to the bx power, is e raised to the bx, or in other words, the exponential function evaluated at b times x. And so it follows then that the antiderivative of the function e to the bx is just using this argument here, very easily shown to be 1 over b times e to the bx power. Okay, so we're going to be using that in the context of this exponential distribution and the derivations that we go through to get various quantities. One specific application of this, there's more than, we're going to be using it in at least two ways, or at least applying it in at least two situations in the context of this exponential distribution. But one way that we're going to use it is to show that the indefinite integral, or the antiderivative of e to the negative x power, is negative e to the negative x power. Now, we're going to start off looking at a special case of, this. In particular, we're going to look at the special case where lambda is equal to 1. So it just, is really not even there. But it is there, but it's equal to 1. So let x be a random variable with PDF given by this expression. So e to the minus x, as long as x is positive, and 0 otherwise. So again, this is a special case of the general exponential distribution. We're going to work with this function first, and then we will generalize the results that we get to the more general exponential distribution at the end of the work. So I'm claiming here that this function f is a PDF, and we can prove that. We can show that it is. Remember that in order for a function to be a PDF, it has to satisfy two conditions. number one, it's got to evaluate to a non-negative number regardless of the point at which you evaluate it. And when you integrate that function over the real line, it's got to integrate to 1. Well, those two criteria are indeed met. If you look at this expression, it's either something positive, which this expression would be positive, or it's equal to 0. It never takes on a negative value. And so this function evaluates to a non-negative value for every real number x. In addition, and now we're going to make use of that mathematical result that I just showed you, the integral of this function over the real line, which simplifies to the integral over the positive part of the real line, in other words, from 0 up to positive infinity, of e to the negative x, is, by the fundamental theorem of calculus, equal to, it's going to be negative e to the negative x, and we have to take the limit of this expression as x goes to positive infinity, and then minus this expression evaluated at 0. So I've done that calculation in the next row, next line here, and so that integrates, or that evaluates to 1. All right, and so those two results then imply that this function f is indeed a valid PDF. Now let's derive the CDF for this special case. So denote the CDF of cap x by uppercase F. Since the sample space of x is the positive part of the real line, the open interval from 0 to positive infinity, it follows that the CDF is equal to 0 if we evaluate it at any value of x that is less than or equal to 0. Because remember, the CDF is a probability accumulator, and so if we evaluate that probability accumulator at any point that is to the left of the boundary, at or to the left of the boundary of the lower boundary of the sample space, then we've not had an opportunity to accumulate any probability, and so therefore it must necessarily evaluate to 0. So we get that just by definition, really. We don't have to do any calculations. For values of x in the sample space of the random variable, in other words, for positive values of x, we've got to do some work. We've got to do some mathematics. All right? But it's not hard mathematics. At such a point, the CDF is equal to the integral from minus infinity up to the point at which we are evaluating the CDF, which is x, okay, of the PDF. And because x is the upper limit of integration here, I can't use it as the variable of integration, or the integration variable, so I'm going to use t instead. Now, this simplifies to the integral from 0 up to x of e to the negative t dt. Now again, using this result, this mathematical result that we talked about, by the fundamental theorem of calculus, this definite integral is just equal to the antiderivative of the integrand here, evaluated at the upper end point, the lower end point, and we take the difference between the two. And so that turns out to be 1 minus e to the negative x power. And so when we put these two results together, we get the fully specified expression for the CDF, which is equal to 0 if we evaluate that CDF at any value at or to the left of the lower boundary of the sample space. And if we evaluate it at any value of x greater than 0, it evaluates to 1 minus e to the negative x. So that is the CDF for this distribution. Now, what are the moments? What are the eventually we want to calculate the mean, the variance, the skewness, and the kurtosis for this distribution, and we're going to be using the expansion formulas to do that. And so we would need the first 4 raw moments. Now, I'm just going to tell you right off the bat that the values of the first 4 moments are 1, 2, 6, and 24 respectively. Okay, the expected value of x, the mean of this special case distribution, is 1. The second raw moment is 2. The third raw moment is 6, and the fourth raw moment is 24. Now, you can find these raw moments in several ways. We could find them via the definition of raw moments. And because this is a continuous random variable, we would need to use integration. We can also compute these raw moments using the moment generating function, which would require two things. Number one, we would have to find the moment generating function, and then two, we would have to differentiate the moment generating function. Now, let's talk about these two approaches. To find the raw moments via integration requires the use of integration by parts. All right? And if you're familiar with that technique, then I would recommend that you try to use that approach to find the raw moments as an exercise. I'm going to leave that for you to do. What I want to do, because this is a really great opportunity for us to utilize the moment generating function to see how that works again, I'm going to use the moment generating function technique to find the first four raw moments. And to be honest with you, this is an example, this is a great example of showing why the moment generating function is so useful, because it's going to be very easy for us to find the moment generating function for this special case of the exponential distribution. It's going to be very simple for us to calculate the derivatives of that moment generating function. And therefore, it will be easy for us to find these first four raw moments using the moment generating function. On the other hand, doing integration by parts, while not terribly difficult, is a little bit more work. And so that's why I'm going to allow you to try that if, in fact, you are familiar with integration by parts. I guess one other way that we could find these values would be to use, for example, the TI-84 calculator, because it would give us these values. But I think that, as we move forward, get further into the material, we want to use approaches that are more analytic in nature, more theoretical in nature. And so what I'm going to do next is first find the moment generating function for this special case of the exponential distribution. So you'll remember that the moment generating function, if it exists, is given by this special expectation, the expected value of e to the tx. And so that expectation is given by the integral over the real line from minus infinity up to positive infinity of e to the tx power times the PDF f of x. This simplifies to the integral over the positive part of the real line from 0 up to infinity of e to the tx times e to the negative x power. Now, using properties of exponents, because remember, the exponential function evaluated at a particular value is just the real number e raised to that power. So this is e raised to the tx power times e raised to the negative x power. So using properties of exponents, I can rewrite this product as the exponential function evaluated at tx minus x power, so the exponents add. And then I can rewrite that just a little bit more to get it into a form that I can then use that mathematical result that we looked at when we started off looking at this distribution. So the integrand here can be rewritten as the exponential function evaluated at negative quantity 1 minus t times x. So if you distribute the negative 1 here across this difference, and if you distribute the x across, then you'll get, again, tx minus x. Now, the reason I do it this way, is because we can think of that negative of the 1 minus t as the value b in that mathematical result. And so we know then that the antiderivative of this integrand is 1 over this b value, so 1 over negative 1 minus t times e to the bx, or negative 1 minus t times x. And to evaluate the definite integral, by the fundamental theorem of calculus, we evaluate, or in this case take the limit of this antiderivative as x goes to as x goes to infinity, we evaluate the antiderivative at 0, x equal to 0, and then take the difference. All right, and so that is what I'm doing down here. I've got to take the limit of this as x goes to positive infinity, and I've got to evaluate this as when x is equal to 0. Notice that I pulled the negative, the 1 over negative 1 minus t out front of that difference. And so when we do that, we get the expression 1 over 1 minus t, which I can also represent as 1 minus t raised to the negative first power, which is convenient, I think, because we're going to be taking derivatives of this function. Now, notice that this, and this is particularly obvious if we look at this next to last expression here, 1 over 1 minus t. Notice that that ratio, that fraction, would not be defined if t was equal to 1. Okay, if t was equal to 1, then the denominator would be 0, and so that would not be defined. But it is defined for any value of t that is less than 0. Okay, so this expression is defined for all t strictly less than, I'm sorry, I said 0, strictly less than 1. And so this expression is defined for all t strictly less than 1, and therefore it exists for all t in a suitably small interval about 0. For example, t being greater than negative 1 and strictly less than positive 1. Now we could pick any small interval as long as the upper endpoint of that interval is strictly less than 1. Okay, but this interval suffices. And the reason we have to think about this is because remember that in order for the moment generating function to exist, this expectation has to exist for all values of t in some interval around 0. It doesn't matter how small that interval is, just some interval around 0. And so we have confirmed that that is indeed the case. We've identified a particular interval around 0 within which this expectation exists for all values of t. And so therefore, it follows that the moment generating function exists for this distribution and is given by either of these expressions. Okay, and I'm going to again write this for convenience sake as 1 minus t raised to the negative 1 power. Now, to find the raw moments of the distribution of x, we differentiate this function, this moment generating function, to evaluate the derivatives at t equal to 0. So by differentiating this function, and then evaluating those derivatives at 0, we generate the raw moments. That's why this is called the moment generating function. Now, with that in mind, the first derivative of the moment generating function turns out to be 1 minus t raised to the negative 2 power. The second derivative is going to be 2 times 1 minus t raised to the negative 3 power. The third derivative of the moment generating function is 6 times 1 minus t raised to the negative 4th power. And then the fourth derivative of the moment generating function is 24 times the quantity 1 minus t raised to the negative 5th power. And so to get the first 4 raw moments, we just evaluate these derivatives at t equal to 0. And so when we do that, we get that the first raw moment is 1, the second raw moment is 2, the third raw moment is 6, and the fourth raw moment is 24. And so these correspond, these are the same values that I gave you back on a previous slide for the first 4 raw moments. Now, if you use the definition for computing the raw moments via integration, again, you're going to have to use integration by parts. So as long as you do it correctly, you'll get the same exact values that we have here. But I'll just tell you, and you'll find this out if you try that approach. And again, I highly recommend that you try it. You're going to find that it's much easier to differentiate. Let me see, sure. I'll keep going back. To differentiate this function than it is to integrate the functions that you would need to calculate those raw moments. So this illustrates why the moment generating function can be so useful because differentiation is typically easier than integration. Now, these raw moments can be used in conjunction with the expansion formulas to obtain the second, third, and fourth central moments. And so doing so gives the following results. The second central moment is 1. The third central moment is 2, and the fourth central moment is 9. And therefore, the variance of this distribution is 1. The skewness coefficient for this distribution is 2, and the kurtosis of the distribution is 9. Okay, and so go ahead and use the expansion formulas to come up with these values for the central moments, and then for the variance, skewness, and the kurtosis. So again, just let me remind you that these are the quantities. We've got here the mean of this distribution being 1, the variance being 1, the skewness 2, and the kurtosis 9. Now, let me remind you that these are the distributional characteristics for this special case exponential distribution, not the general exponential distribution. What we're going to do next is generalize the results to the general exponential distribution. And so to do this, what we're going to do is we're going to define a new random variable, which we'll call y, using or based upon the special case exponential random variable x that we've been working with. In particular, we're going to transform this special case random variable, this special case exponential, by multiplying it by lambda, where lambda is a positive fixed constant. So this new random variable, y, is equal to the special case random variable x times lambda. And so now we're going to find the CDF of the distribution of y. We'll then find the PDF of y. And we will show then at that point that this new random variable y has that general exponential distribution form that we started off with. And then from there, we'll be able to leverage what we've the work we've just done in deriving the various distributional characteristics of x, and translate that into analogous values. Well, we'll be able to get the distributional characteristics for the distribution of y. Now, the sample space of x, the special case exponential, was the positive part of the real line. By multiplying x by lambda, which is positive, we have not changed the sample space. So the new random variable y has the same sample space as x, and in particular, the positive part of the real line. Now, the first thing we're going to do in finding the distribution of y is we're going to find the CDF of the new random variable y. Since we've already used uppercase F, remember, is the CDF of the special case random variable x. Now, that notation has already been used, so we cannot use that now. So let's denote the CDF of y by capital G. Now, because the sample space of y is the positive part of the real line, by definition then, because G is a probability accumulator, it must be equal to 0 if we evaluate it at any value of y that is less than or equal to the lower boundary of that sample space. So again, we get that for free. That's basically by definition, all right? And so we know that much about the CDF. For values of y that are positive, by definition, let me see if it can let me highlight. No, it won't. The CDF evaluated at y, by definition, is equal to the probability that the random variable y takes on a value less than or equal to the argument at which we're evaluating the CDF. And because y is equal to lambda times x, I can just replace y by lambda times x in this probability statement. Now, I want to get x by itself, and I can do that by dividing both sides of this inequality by lambda. And because lambda is positive, the direction of the inequality stays the same. All right? And so we get that the CDF evaluated at y, where y is positive, is equal to the probability that the random variable x is less than or equal to y over lambda. But now this probability is just the CDF of x evaluated at y over lambda. Now, because y is positive, y over lambda is positive, and so that for such a value, the CDF of x is equal to 1 minus the exponential function evaluated at that argument, which is the negative of that argument, which is y over lambda. So remember, we derived the CDF of x, and this is the CDF of x evaluated at such a point. And so putting these two results together, we have now the fully specified expression for the CDF of the new random variable y, right? It's going to be equal to 0 if we evaluate that CDF at any value of y less than or equal to 0, and it's 1 minus e, or the exponential function evaluated at negative y over lambda for any positive value of y. Next, denote the PDF of y by lowercase g. All right, if we're going to use uppercase g for the CDF, we'll use lowercase g for the PDF. And since the space of y is the positive part of the real line, we know that for any value of y that is less than or equal to that lower boundary point, that the PDF must evaluate to 0. So for any value of y not in the sample space of the random variable, the PDF evaluates to 0. For values of y in the sample space, we can get the PDF from the CDF by differentiation. You'll remember when we first started talking about random variables and their distributions, and in particular, when we talked about continuous random variables, we said that there's a relationship between the PDF of a continuous random variable and its CDF. And in particular, the PDF is equal to the derivative of the CDF. And so we know the CDF, we just derived it. And so for values of y that are positive, we can evaluate, get the expression for the PDF by differentiating the CDF, the expression that the CDF takes on. And so when you do that very simple calculation, taking the derivative with respect to y, the expression for the PDF is equal to 1 over lambda times e to the negative y over lambda. So putting those two results together, we get the fully specified expression for the PDF, for the distribution of y. It's equal to 1 over lambda times the exponential function evaluated at negative y over lambda for values of y that are positive, and it's 0 otherwise. If you go back and look at the expression that we started off talking about with the exponential distribution, that general form of the exponential PDF, you'll see that this is the exact same thing. The only difference is here we're using y. Back then we used x. So this is the general form of the PDF of the exponential distribution. And remember that the parameter lambda, which shows up there and also there, that parameter must be positive. Now, to find the various characteristics for this general exponential distribution, we can make use of what we have learned about those characteristics for the special case exponential distribution and in conjunction with the linearity property of the expectation operator. So in other words, we're not going to go back and use integration or find the moment generating function for the distribution of y. We could to find these distributional characteristics of y, but we don't need to. We're going to, because there's a relationship that we'll see here. There's a relationship between the distributional characteristics of x and the distributional characteristics of y. So, for example, to start off with, the first raw moment of the distribution of y, the expected value of y, which is also the mean of the distribution of y, is equal to the expected value of lambda times x. Because lambda is a constant, we can pull it out of that expectation. The expected value of x was found to be 1. And so this shows that the expected value of y is equal to lambda. All right? Now the variance is the second central moment. All right? The variance is given by this expectation, the expected value of the square of y minus the expected value of y. Now, y is equal to lambda times x. And we have just shown that the expected value of y is equal to lambda times the expected value of x. I'm not going to put in, I could put in 1 here, but I'm just, what I've done here, notice that I can, and I've left out a step or two, but I can factor the lambda out of this difference. But when I do, I have to square it because we're squaring that difference. And so I have the expected value of lambda squared times the difference, or the square of x minus its expected value. So lambda, and then because lambda squared is a constant, and because of the linearity property of the expectation operator, I can pull that out as well. So I have lambda squared times the expected value of the square of x minus its expected value. And this is the reason I wanted to leave this way, because you can, I'm sure that you immediately recognize that expectation is just the variance of x. Well, we showed that the variance of x is equal to 1. And so the variance of y is equal to the square of the parameter lambda. Now, once we have that, then we know that the standard deviation of y is going to be the square root of the variance. And so the square root of the distribution is equal to lambda. Now we can find the third central moment of y using an approach very similar to what we did with the second central moment. Again, we can factor out the lambda, and now that, because we have an exponent of 3 here, the lambda is cubed, and so then we can pull that out because of the linearity of the expectation operator. And so we have the lambda cubed times the third central moment of the distribution of x, which we showed to be 2. Okay, and so the third central moment of the general exponential distribution is 2 times lambda cubed. Now, to get the skewness, we divide this third central moment by the variance of y raised to the 3/2 power. Right? The variance of y was lambda squared, which we showed on the previous slide here, I'm showing. All right? And so when we raise that to the 3/2 power, we get lambda cubed. And so the skewness of the general exponential distribution is 2. And then finally, we can find the fourth central moment of the distribution of y. Again, by factoring out the lambda, this time it's raised to the 4th power. And so we have lambda to the 4th times the 4th central moment of the distribution of x, that's special case exponential. We showed that to be 9. And so the 4th central moment of the distribution of y is 9 times lambda to the 4th. To get the kurtosis, we divide that 4th central moment by the square of the variance. The variance was lambda squared, so we square that, we get lambda to the 4th, and so we've got lambda to the 4th upstairs, we've got lambda to the 4th downstairs. They cancel out, and so we get a kurtosis of 9. So let's put all these results together. To summarize these findings, denote the PDF and the CDF of the general exponential distribution by lowercase f and uppercase f, respectively. And we'll let x have an exponential distribution with the parameter lambda. So just let's not get confused here. Previously, we used x as a special case exponential, but now just to restate all these results, to bring everything together, right, and to state things in their generality, I'm going to let x have this general exponential distribution with parameter lambda. Then the PDF is given by this expression. The CDF is given by this expression. Structurally, the parameter lambda is a scale parameter of the distribution. Okay, the parameter lambda is also, we've shown, to be the mean of the distribution. it's the standard deviation of the distribution, and the square of lambda is the variance of the distribution. And not only that, we know that the skewness coefficient for the general exponential distribution is 2. Now, because this does not depend on lambda, what this tells us is that every exponential distribution has a skewness coefficient equal to 2. The kurtosis is equal to 9. Because that does not depend on lambda, this tells us that every exponential distribution has a kurtosis of 9. So the mean of the distribution is lambda. Okay, that does depend on lambda, obviously. All right. The variance is lambda squared. The standard deviation is lambda. So the mean and the variance and the standard deviation depend on the parameter lambda for the general exponential distribution, but the skewness, neither the skewness nor the kurtosis depend on lambda. Okay, so that is all we're going to say about the exponential distribution, at least for now. I will tell you that the exponential distribution, one of its applications is in the context of survival analysis and life testing. And in particular, it's a good distribution to use when you're, for example, modeling the lifetime of manufactured components that are not subject to wear and tear. If the random variable x corresponds to the time until failure of a manufactured component that is not subject to wear and tear, then it can be shown that the exponential distribution is a good model. It's a good theoretical distribution to use to model the lifetimes of such components. And so, as an example, components that wear out, but they fail at some point, but it's not due to physical wear and tear necessarily. Might be electrical components, maybe electronic circuits and things like that. So the exponential distribution would be a good distribution to use to model the lifetimes of those kind of components. A component that would not be suitable for modeling via an exponential distribution might be tires or ball bearings. Really anything that is subject to wear and tear, which eventually leads to failure of the product. Okay, so that's all we're going to say about this distribution. I think that we covered a lot of ground here. We have looked at a very important, in this last distribution we looked at a very important continuous distribution. We've derived the moment generating function for that distribution. We have used the moment generating function to generate the raw moments of the distribution, from which we calculated the various distributional characteristics that we're usually interested in with distribution. So we've covered a lot of ground, and we've done some things that I think are going to be very helpful to you as we continue through the course and you're doing lab assignments.